Chapter 4.2, exercises 41 through 54. This section has to do with trigonometric functions of acute angles. And we're going to go over the odd-numbered set problems here and then leave the even-numbered for you to do. In exercises 41 through 48, find the acute angle theta that satisfies the given equation. Give theta in both degrees and radians. You should do these problems without a calculator. Well, in this case, this first one, we have sine theta equals 1/2. And usually when we look for problems what we're looking to do without a calculator, we're looking for special right triangles. And special right triangles, there are two kinds of them. There is the 45-45-90 triangle, which looks something like this. And so you have a 45-degree angle here. You have in the corner, the lower right corner, 45 degrees. And then the upper right corner, you also have 45 degrees. And for this type of triangle, you can look at the ratio of the sides, which is found by taking x, and the hypotenuse is x square root of 2. And the problem we're going to be working with here, problem 41, is going to be a different type of special right triangle, where you have we call a 30-60-90 right triangle. So we have 30 degrees here in the lower left, and to the right, upper right, is going to be 60 degrees. And then the right side, the opposite side, is going to be x. That's going to be our opposite side. Our hypotenuse is going to be equal to 2x, and our adjacent side is going to be equal to x square root of 3. So in this, where sine equals 1/2, sine theta equals opposite over hypotenuse. Well, in this case, in order to get opposite over hypotenuse, we're going to have what is the ratio in any of these special right triangles that gives us a ratio of 1/2. Well, for that, we're going to have x over 2x, which equals 1/2. And so what that means is this angle, 30 degrees, the sine of 30 degrees is equal to 1/2. And so if we're asked what the angle is that gives you whose sine of that angle is 1/2, our answer is going to be 30 degrees. It says find theta in both degrees and radians. Well, the relationship to degrees and radians is that there are 180 degrees for every pi radian. And so to convert this, so 30 degrees is one of our measures, and to convert this 30 degrees into radians, there's a 30 degrees times, we take pi radians over 180 degrees. What that's going to do is we have 30 divided by 180, we're going to get pi over 6 radians. So our angle measure in radians is pi over 6. Next, let's go to problem 43. The cotangent of theta is 1 over square root of 3. Well, in this, we're going to be looking at a type of special right triangle And we're not sure at this point which one it is. It could be either a 30, 60, 90 like this. Okay, I'm drawing a 30, 60, 90. It's not too accurate. Or it can be a 30, 60, 90 drawn in this kind of orientation, where this is the 60. So it can be in either orientation. For either orientation, we're going to have x, and the hypotenuse here for this 30-degree angle is going to be 2x, and x square root of 3. And I'm going to make this other steeper triangle. I'm going to trace this in red, kind of get a color-coded explanation. So our angles here in red is going to be 60 degrees. All right, 60 degrees. And then our sides are going to be in red here below. X, our hypotenuse again, just like the blue triangle, it's going to be 2x. And our opposite side is going to be x square root of 3. And then in blue, of course, our opposite is x, and our adjacent is that one. And our red one, of course, x is our adjacent. Well, cotangent, tangent theta equals opposite over adjacent. And so a cotangent is going to be reciprocal of tangent. So cotangent theta equals adjacent over opposite. And that's going to be 1 over square root of 3. And so let's look at this red one here. If we have adjacent over opposite, so we're going to say cotangent of 60 degrees, and we're talking about this red triangle now, it's going to be equal to adjacent over opposite, where our adjacent side is x, and our opposite side is going to be x square root of 3. And so x over x cancel, so we have 1 over square root of 3. Therefore, what that means is that in order for the cotangent of an angle to be 1 over square root of 3, theta has to equal 60 degrees. And in radians, that's going to have to be 60 degrees times pi radians over 180 degrees. Degrees over degrees cancel, and 60 divided by 130 is going to be pi over 3, and that's radians. Next, on problem 45, we have the secant of theta equals 2. Well, secant of theta is equal to 1 over cosine theta. And since cosine theta is equal to adjacent over hypotenuse, then secant theta is going to be equal to hypotenuse over adjacent. All right. Let's go look at our special right triangles. I'm going to go ahead and pull out a blue triangle here where we have 60 degrees. we have our adjacent side is x equals adjacent. Our hypotenuse is going to be 2x. And our opposite side is going to be x square root of 3. Now, if we look at this value of 2, we're looking at where hypotenuse over adjacent equals 2. Well, if we have the secant of this angle, 60 degrees, is going to be equal to our hypotenuse. Well, I'll say just secant theta, because we haven't identified what is. Secant theta is going to be equal to our hypotenuse in this case, which is 2x, over our adjacent side, which is x. Well, x over x cancel, so we equal to 2 here. So the angle that it's going to take for this equation to be true is that secant of what angle? 60 degrees is going to be equal to 2. So therefore, theta is equal to 60 degrees. And if we go back to our problem 43, that is going to be equivalent to, in radian measure, pi over 3 radians. So that would be, those would be our answers, both in degrees and radians. Next, problem 47. The tangent of theta equals square root of 3 over 3. And for that, tangent theta equals opposite over adjacent. And we can try a couple different angles. We'll try the 60-degree angle we worked with last time. So we draw this theta here equals 60 degrees, and our adjacent side down here is equal to x. Our opposite side is equal to x square root of 3, and our hypotenuse is equal to 2x. What we're going to have for the tan of 60 degrees is going to be our opposite, which is x square root of 3 over x, which simplifies to square root of 3. Well, we want to find square root of 3 over 3. That's going to be less than 1. Here we have a greater than 1. In fact, if we rationalized the numerator, we would get times square root of 3 over square root of 3. We would get 3 over square root of 3. Well, we need square root of 3 over 3. So for that, I'm going to superimpose my 30, 60, 90 degree triangle like this. And here it is, I'm drawing in red. And for this one, I'm going to put theta equals 30 degrees. And we have our opposite side is x. Our adjacent side equals x squared root of 3. So tangent of 30 degrees is going to be x over x square root of 3, which simplifies to 1 over square root of 3, and rationalizing by multiplying by square root of 3 over square root of 3, we get square root of 3 over 3, which is what we're looking for. Therefore, the theta is going to be half, for this relationship to be true, is going to be half, is going to have to equal 60 degrees. And in radians, we're going to have to be equal to pi over 3 radians. So these are the odd number of problems in this set worked out, this set 41 through 48. Good luck on the even number problems. We're going to go on here to the next set of problems. Exercises 49 through 54, solve for the unknown shown. Here we have x. What we're looking for is we have an x and a 15 to identify properly which elements we have. Well, here's 34 degrees sitting over here in the lower right corner. If we go precisely opposite that 34 degrees, we see that 15 is the side that is opposite. Okay, 15 is opposite, and above here, x is our hypotenuse. So what we have is the sine of 34 degrees is equal to our opposite, which is 15, over our hypotenuse, which is x. And so to solve, we can multiply both sides of this, solving for x, we multiply both sides of this equation by x, so we get x sine 34 degrees equals 15x over x. And we have a cancellation of x over x on the right side. And now we have x sine 34 degrees is equal to 15. And solving for x, if we divide both sides of this equation by sine of 34 degrees, we have a cancellation of sine 34 degrees over sine 34 degrees to equal 1. So x is going to be equal to 15 over sine 34 degrees. I want to tell you what I did in this exercise set. Is the exercise set in the book said solve for the variable shown. Well, when you have a single variable in an equation that you are able to solve for, that is really not a variable. A variable is something that varies. So I properly term this thing we're solving for as an unknown. So the thing doesn't vary at all. If you had an equation with x and y, then I think we could properly call x a variable. But in this case, x is an unknown. It is something. We just don't know what it is yet until we solve it. So, and now the last thing that they do in the book also is to put that in our calculator, and we are already in degrees. Let's make sure we're in degrees. Check settings, 5, document settings, in degrees. We escape out of here, go to get our calculator page, control division sign, we have 15 over sine of 34 degrees. So sine 34 degrees. And so we get 26.82 and approximately 26.824. So we'll do the 3 decimal places. Okay, this one on top is an exact answer. The one here on the bottom, the squiggly line, squiggly equal, is the decimalized approximation. Next odd number problem is 51, and we're given this triangle, and we have 57 degree up here in the upper right corner, and to go to the opposite side, we find 32 degrees. So 32 is our opposite side in this triangle, and this y is adjacent to that angle. So y is our adjacent side. And so we look for the ratio that has to do with adjacent and opposite, and that would be tangent. Well, tangent theta, 57 degrees, is going to be equal to our opposite, which is 32, over our adjacent, which is y. But the cotangent is the reciprocal of tangent, so the cotangent of 57 degrees is going to be equal to y over 32. Now, why is this helpful to us? Well, the reason it's helpful to us is that I find it easier to solve for an unknown that's in the numerator as opposed to the denominator. So if we multiply both sides of this equation by 32, we have, on the left side, we have 32 cotangent of 57 degrees is equal to y times 32 over 32, which we designed to equal 1. So y equals 32 cotangent of 57 degrees. Okay, so what I'm going to do here is box this in as our correct answer. The book has as a correct answer 32 over the tangent of 57 degrees, which is equivalent. So 32 times cotangent. If we didn't have the cotangent key available, we could do 1 over tangent and get the same. So 57 degrees, we're going to get 20.781. So, and that's going to be y equals approximately 20.781. Okay, next, and this will be our last problem in this set. We have problem 53, and we have this triangle. Well, very similar orientation to the last one we looked at, except 35 degrees, and our opposite side is going to be 6. And y is our hypotenuse. And so we look for the ratios that involve hypotenuse and opposite. Well, we know that sine 35 degrees is going to be equal to our opposite, which is 6, over our hypotenuse, which is y. But the reciprocal ratio of sine is cosecant. Cosecant of 35 degrees is going to be y over 6. And if we cross multiply, or multiply both sides of the equation by 6, we get 6 cosecant 35 degrees is equal to y times 6 over 6. And 6 over 6 cancels, so y equals 6 times cosecant 35 degrees. And it so happens that the way the book has the answer, the book answers the question as 6 over sine 35 degrees. And these things are exactly the same. And so I'm just going to leave it in the cosecant form, but the sine form is equally sufficient. So 6 times cosecant 35 degrees we have 10.461 or 4607. I'll call it 10.461. Anyway, that's a set of odd numbered problems here. Good luck on your even number problems as a demonstration of your learning. To me, the hardest part of this video lesson was the first part we went over, really having to reconstruct and figure out these special right triangles. So good luck to you, and thanks for viewing.